This video is about rational and irrational numbers. So what are rational numbers? Well, rational numbers are all numbers that can be written in the form of P by Q, where P and Q are all integers and Q is not equal to 0. Okay? These are the two conditions for a rational number. So irrational numbers must be all numbers that cannot be written in the form of P by Q, right? I'm of course with these conditions applied. So therefore we can conclude if a number can be written in P by Q form, it can be either rational or irrational. However, to differentiate is with the condition. The conditions being P and Q are integers, P and Q are integers, and Q is not equal to 0. All numbers can be written in the form of P by Q, but not all numbers can be written in the form of P by Q when P is an whole number or an integer, right? For example, pi can be written in the form of P by Q, but we do not have any integer value, right? We can write it in another form. And now the second clause is because any number divided by 0 is undefined. It is not infinity, it is undefined. Like you cannot say infinity, this is wrong. This is correct, right? So these are rational and irrational numbers. Now we're going to look at the two forms of irrational numbers. So when you talk about irrational numbers, you have surds and other irrational numbers. Your other irrational numbers include things like pi. I is an imaginary number, right? It's not even a real number. Rational and irrational come under real numbers. And then you have imaginary numbers and all of these come under the broader numbers, which is the universal set, right? This is our whole set. This is how it's divided. And then rational numbers can be divided into negative numbers, positive numbers, integers, etc. Right? So pi is irrational because it can't be expressed in P by Q, where P and Q are integers. Now surds are numbers like root of 2, root 3, root 5, root 6, root 7, root 8, root 10, etc. Now you may notice that I've skipped root 1, root 4, and root of 9. Now this is because root of 1 is 1, root of 4 is 2, and root of 9 is 3. How do we know this? Because 1 square is 1, 2 square is 4, 3 square is 9. So these can be written in the form of P by Q, which is 1 by 1, 2 by. Root of 1 can be written as 1 by 1. The root of 4 can be written as 2 by 1. Root of 9 can be written as 3 by 1. Right? So, however, root of 2 cannot be written in the form P by Q. The closest you'll get to two numbers that multiply each other, with each other to make 2, is going to be 1.414, right? But this is only going to give you 1.99999. It's not never going to give you 2. but most modern calculators give you 2, right? So root 2, root 3, root 5, root 6, root 7, root 8, these are all surds. Now we're going to look at simplifying surds, right? Let's consider root of 6. Now 6 can be written as 2 into 3, right? 6 is equal to 2 into 3. So root of 6 is equal to root of 2 into 3. Now root, we know a times b, or can be written as a, a root of a times b, right? Erase this, yeah. Root of a times root of b can be written as root of a b. So we can work this backwards as well. That root of a into b can be written as root of a times root b. Actually, let's go over the rules for surds once. So when you come look at surds, let's take root a times root b, root a divided by root. These are very similar because multiplication and division are quite similar. Root a times root b can be written as root of a into b, and root a by root b can be written as root of a by b whole. Right? Now, when we look at root of a plus b, root of b, or root of a minus root of b, cannot be written as root of a plus b, and this cannot be written as root of a minus b. Let's take a couple of examples to show this. Let's take root 4 times root 9, right? So root 4 times root 9, following this rule, we can write it as root of 4 times 9, which is 36, right? Which is 6. And doing anomaly, we get 2 times 3, which is also 6. So that checks out. Let's do the same thing here. Root 4 by root 9 can be written as 2 by 3. Let's do it the other way as well. Root 4 by root 9 can be written as root of 4 by 9 whole. So 4 by 9 can cancel to, no, root 4 by 9 can't really cancel, but root of 4 by 9 is the same as 2 by 3, because 2 by 3 times 2 by 3 will give you 2 into 2 by 3 into 3. This is 4 by 9. Right. So that's how we get root 4 by 9 is equal to 2 by 3. This checks out. Now when we add, we look at adding, we have root 4 plus root 9, which is 2 plus 3, and that gives you 5. However, if we try to add them up, we get root 4 plus 9, and that's root 13, which is an irrational number. It's a surd. While root 4 plus root 9 gave you a whole number. Okay. Let's look at root a minus root b. Of course, here we'd have to take it reverse, root 9 minus root 4. Otherwise, we'd be dealing with imaginary numbers. So root 9 minus root 4, you get 3 minus 2, which is 1. And the other way, you get root 9 minus 4, which is root of 5, which is again irrational. So that proves that the root of a plus root of b is not equal to root of a plus b, and likewise for subtraction. Well, now root a times root a is essentially root a square, right? Root a square. And now you have a square root and you have a square, so that's going to cancel. So you're going to get a. So therefore root a times root a is just a, right? And a times a to the power of 1 by 2 is the same as writing root of a. That is useful when we consider indices. Right? Uh, this is these are the elementary rules for what do you say, for surds. Right? So coming back to our problem here, root 6 can be written as 2 times 3, so root 2 times root 3. So this can be written as, looking at our rules from earlier, root 2 times root 3, right? This is surd, quite easy. Root 2 times root 3, it can't be simplified, so this is the simplest form. Now, when we consider something like root of 8, okay, 8 can be written as 2 into 2 into 2, or 2 into 4, right? Or 8 to 1, but that doesn't get us anywhere. We're not going to consider this. So let's consider 2 into 4, because that's the simplest, right? Root of 8 can be written as 2 into 4, so that's root 2 times 4, root of 2 times 4, and root of 2 times 4 can be written as root 2 times root 4. Now you may notice that root 4 is it's a perfect square. 4 is a perfect square, so we can write this as root 2 times 2, and that's essentially 2 root 2. 2 root 2 basically means 2 times root 2. That is the same as writing 2 into root 2. Right? Let's just write that here. Root of a times b is equal to b root a. Right? So that's simplifying surds. Now, in our syllabus, we also have rationalizing the denominator. It's a very important topic, rationalizing the denominator. What this means is your fraction can sometimes, when it's an irrational number, we see rational numbers have to be written, the p and q need to be integers. But irrational numbers, they can sometimes have surds in the place of q. Right? So let's consider a number 2 root of 3. 2 by root of 3. Sorry. Now, 2 by root of 3. The problem is dividing by the root of 3 is really difficult, especially in without a calculator, right? Because you're going to have a really long string of numbers to divide with. So, we know that multiplying, if you want to keep a fraction in the same form, right? 1 by 2 is the same as 2 by 4. But what have we done here? We've done 1 by 2 times 2 by 2, right? Which is 1 times 2 by 2 times 2. So we're multiplying both the numerator and the denominator with the same number, right? So in the same way, when we look at our rules, we have root of a times root of a gives you a. So that's it, removing this root, at least in the denominator. It's much easier to handle when it's in the numerator. So we're going to apply that concept here. So when you have a number, when there's a surd on its own in the denominator, what we do is we take the fraction, write it down, and we multiply it by the root in the denominator. So 2 times of root 3 divided by root 3 times root 3. So this will give you 2 root 3, looking at our a times root of a times b is same as b root a, and root 3 times root 3, looking at root a times root a is equal to a. We know that it is 3. Now this is a much easier to sum to solve, especially if we had a number rather than 2 by root 3, right? 2 by root 3. Suppose we had 3 by root 3, right? In this case, if we had 3 by root 3, then in this here we would be able to cancel the 3's. So our final answer would be root of 3. And 3 divided by root of 3 is quite complicated. But just finding the square root of 3, you've eliminated a step. And you don't have to do that many calculations. Now sometimes you can also get fractions like this in the form of a plus b by c plus d, or sometimes in the form of a plus b by c plus root d. So let's consider a fraction in the form of a by b plus root of c. So looking at a fraction like that, let's take 2 by 4 plus root 5. Now when we look at something like this, we don't seem to have any of those rules here. None of our rules seem to apply because we said addition, you can't take that under the bracket, right? I mean, writing root 16 plus root 5 is not the same as root of 16 plus 5, right? So root 16 plus root 5 is not the same as root 21. So what we're going to do here is we're going to look at identities. So when you have a plus b whole square, right, it's not going to be a square plus b square. But we're going to expand this bracket. So a plus b whole square is the same as a plus b whole times of a plus b. So here, what's going to happen is you're going to multiply a with a plus b, and you're going to multiply b with a plus b. It looks very messy that way, but a lot of people find it easier when it's represented diagrammatically like that. So a times of a plus b, this is simple expanding the brackets, you get a square plus ba plus b times of a plus b, you get b plus ba plus b square. Now ab is the same as ba, so a square plus 2ba plus b square. And we expand the brackets. Okay. So a plus b whole square is not a square plus b square, but a square plus b square plus 2ab, right? This is very important. Now we're going to look at a minus b square as well. So a minus b square is not a square minus b square. We're going to use the same, apply the same concept as earlier. So we're going to write it in its full form. So that's a minus b whole times of a minus b, and a minus b, we can write this as a times of a minus b. And now here you don't write plus b but minus b. You have to consider this, the minus sign here when you are writing your number. So minus b times of a minus b, even when multiplying. Here I'm going to get a square, and again you consider the negative sign, so you get, it's not plus ba, rather it's minus ba. Right. Likewise here you consider the negative signs, you get minus ba and minus b and minus b, you get plus b square, because minus times minus equals plus. Go check out our last video for more details. Right. So a square minus ba is the same as writing, we ignore the signs, we do ba plus ba, which is 2ba, and we see they both have minuses, so it's minus ba minus ba, it's minus 2ba. Go check out our video on the number line. So this is a square plus b square minus 2ba. Right, so a minus b whole square is Not a square minus b square, but a square plus b square minus 2ab. And the last identity we're going to look at today is a plus b times of a minus b. Now here, and mind you, these are all very fairly common identities that you get in the exam. So these are important to know and understand the logic, right? So we're going to apply the same concept here, right? We're going to do a plus b, a times of a plus b, minus b, again consider the minus sign, times of a plus b. So you're going to get a times of a square, a times of b plus ba, minus b, consider the negative sign, so minus ba minus b times b is equal to minus b square, right? Now plus ba minus ba is going to cancel. It's going to get a square minus b square. So that's our third identity. Okay, so now that we know this, let's come back to our problem here. So we want to remove this root, right? And we have another number here. So this is in the form of a plus b, where a is equal to 4, b is equal to root 5. Now we want to ensure that b is squared, so we can eliminate the root, the square root. Right? So what by multiplying it with what gives us the simplest expression in the denominator, right? See, all you can do all of these, but the problem is you have this extra term plus 2ab minus 2ab, and it's not b squared. It's not b squared, right? It's just b. So that means that you're going to have a root in the answer, which completely defeats our purpose. But here, there is no b in its own. It's all 2, right? It's all b squared, b to the power of 2. So we're going to use the we're going to use 4 minus root 5 in this case. So you're going to do 2 times of 4 minus root 5. Now mind you, you're going to have to put this in brackets, and likewise with the denominator, 4 plus root 5 whole times 4 minus root 5. Now let's expand the brackets. You get 2 times of 4, which is 8, minus 2 root 5. And now let's expand the brackets here. A square minus b square, use our identity, so we don't have to expand it and then simplify. So a square, a is 4, so a square is 16, minus b square is 5. So you get 8 minus 2 root 5 by 11, which is much, much, much simpler to solve than this. Right? And sometimes you may be lucky and you may be able to cancel, right? So now if you have 2 by 4 minus root 5, all you'd have to do is, rather than multiplying with 4 minus root 5, this time you're going to multiply with 4 plus root 5, right? Because we want to have that a plus b times of a minus b. In this example here, we have a plus b, we have the a plus b term, we don't have the a minus b term. In this example, we have the a minus b term, we don't have the a plus b term. Right? So 4 minus root 5, we have 4 plus root 5. The final answer is going to be 8 minus 2 root 5 by, sorry, 8 plus 2 root 5. My apologies. 8 plus 2 root 5 by 11. Be very careful, your numerator will change because there's 2 times of 4, 8, and 2 times of plus root 5, not negative root 5. So 8 plus 2 root 5. Right, so that's how you rationalize the denominator.